All right, so in this video I want to talk about something, hopefully that will clear up a little bit of confusion about the way sometimes chemists will refer to Ka. All right, so a lot of times people refer to this term Ka incorrectly when referring to bases. So to illustrate this point, I'm going to show you this little shot from this very common website. It's a chemistry related website, pKa's, and they're talking about methylamine. And when they report the pKa, they report it as 10.6. All right, and what I'm going to tell you is that this is actually incorrect. This is not literally the pKa of methylamine. All right, what this number actually is the pKa of the conjugate acid of methylamine. All right, so let's talk about why they do this. Okay, so first of all, let's talk about why it's technically incorrect to say that that is the pKa. So whenever you say the pKa of a compound, all right, remember, Ka and pKa refer to how strong or how willing something is to act as an acid. All right, so when you see the pKa of some compound, that means treat that compound as if it's an acid. All right, and when you're doing that, you should show that compound reacting with water and doing what acids do. Acids donate H pluses. All right, so literally that's what an acid would do, and a Ka of that particular acid would follow this particular format, where this is the conjugate base and this is the acid form down here. If you say the Kb or the pKb of some compound, it means treat that compound as if it's a base. All right, so for example, if you show ammonia acting as a base, it would react with water and make this conjugate acid right here. And we could come up with a Kb expression and represent it this way. All right. So why is this right here technically incorrect? Okay. Notice that it said the pKa. All right. So if we're talking about the pKa of methylamine, what that literally would mean is treat it as if it's an acid. All right. Which would mean let's show it in this equation right here. And if this were to act as an acid, it would be donating one of its H pluses, all right, which, by the way, methylamine would not be inclined to do. All right, but if it did, if we're talking about its pKa, this is literally the equation that you would be talking about. All right, and so the Ka from this equation would be this right here. And what I can tell you is that there is no way that these ratios right here would be this number. All right, and that's what that number would have to be for its pKa to be 10.66. All right, so this is wrong. All right, so what do they actually mean when they say that the pKa of methylamine is 10.6? What they really mean is that the conjugate acid of methylamine, the pKa of that conjugate acid is 10.6. All right, so if we take the conjugate acid, so if this is methylamine, its conjugate acid would be this right here. And that conjugate acid, if it acts like an acid, can donate an H plus to water in this equation right here. And if we show the Ka expression for this equation right here, it would be like this. All right, so we take the things on the right, we put them up top. Take the thing on the left, we put it on the bottom. We don't worry about water. And these ratios right here would actually be about 10 to the minus 10. Okay, and again, why is this? Remember, when you're going from a pKa to a Ka, it's basically the Ka is going to be 10 to the negative of this number. All right, so that's why I'm just estimating this number. All right, and this is what is actually correct. All right, so why is it that chemists commonly do this thing where they refer, when describing the strength of a base, why do they give the pKa or the Ka of its conjugate acid? All right. All right. After all, we already have terms used to describe the strength of a base. All right. Remember, when we were talking about the strength of an acid, we talked about Ka's and pKa's, because that literally talks about how well an acid will donate a hydrogen. And we have pKb's and Kb's, which refer to a base's ability to accept a hydrogen. Why don't we talk about the strength of a base by referring to its Kb rather than talking about the Ka of its corresponding conjugate acid? And the answer is that it allows us to compare an acid to another base using one scale. All right, so I'm going to give an analogy here that hopefully makes this make sense. So I'm going to use some terms that hopefully everyone should be familiar with, which is generosity and greediness. All right, so what is hopefully you realize that generosity is a lot of times related to greediness. All right, but literally when you're talking about generosity, you're talking about the willingness of somebody to give away something that they currently have. All right, and when you're talking about greediness, what you're talking about is the eagerness for somebody to want something that they currently don't have. All right, so to make an analogy, when somebody has money, all right, that's like considering that thing the acid. All right, just like an acid is something that currently has the H plus. All right, when someone doesn't have money, all right, that is like the conjugate base. All right, so remember the conjugate base is what's left over once the acid gives up the H plus. All right, so what I'm going to show here is I've got three different people, Tom, Bill, and Sam. All right, Tom is the most generous. All right, so when we're showing what happens when somebody is very generous, it would be like showing an acid reaction. You're showing that person giving away money. All right, so Tom being generous would look like this. Bill doing what he would do to be generous looks like this, and Sam would look like this. All right, and so what we know is that Tom is the most able or the most willing to give away money. That's why he rates very high on the generosity scale. All right, Bill is somewhere in between. Sam is just not very willing to give away his money. All right, so the thing about this, let's consider the greediness scale. All right, this would be like if we took Tom, Bill, and Sam and we said, okay, let's take Tom, Bill, and Sam and compare their eagerness to grab onto money. All right, well, here's the thing. Do we really have no idea, or could we use some intuition about their generosity to make some predictions about how greedy these exact same people would be if they didn't have money? All right, and hopefully you'd realize that Tom is the type of person that very easily parts with money. All right, so that means when Tom doesn't have money, he's probably going to be not that greedy. All right, if he's perfectly willing to give away money, he's not that eager to get it back. All right, Sam, on the other hand, is very low on the generosity scale. All right, he really likes to hold on to his money. All right, so therefore, when Sam doesn't have money, he's going to be, by comparison, more eager to grab onto it. All right, so hopefully you would realize that things, when somebody has money and they score high on the generosity scale, what that would mean is that same person without money would score low on the greediness scale. So what can we do with these scales? All right, well, one thing that we could do with these scales is make predictions about what would happen if you mix certain things together. And the reason I'm using this analogy is this is what we end up doing in chemistry. We're going to make predictions about what would happen if you mixed certain acids with certain bases. All right, would that base be strong enough to take that hydrogen away from a certain acid? All right, so let's take a look at these two examples. All right, Tom with money and you mix him with Sam without money. Can we make a prediction about whether Sam would take the money, or would Sam be inclined not to take the money? All right, well, let's take a look here. All right, well, Tom, we can see here, is very generous. All right, Tom gives away his money very easily, and Sam, well, notice that what we're showing here is Sam without money. All right, well, Sam is very high on the greediness scale. All right, so we take someone who's very generous and we mix him with somebody who's very greedy. All right, notice the person that's generous currently has the money. The person that's very greedy currently doesn't have the money. All right, would something happen? Absolutely. All right, Tom would lose his money to Sam. Sam would take the money away. All right, but let's compare something else. All right, Bill with money, all right, compared to Tom without money. All right, well, we can see here Bill is kind of moderately generous. All right, but we can see here that Tom without money, he is extremely ungreedy, or sorry, he's extremely ungreedy. All right, so you take somebody who's not very greedy at all, and you mix him with somebody who's moderately generous, and nothing would be, nothing would happen. All right, and that happens because Tom is so incredibly ungreedy. All right, but ask yourself, did we need to have two separate scales to make these predictions, or Or could we have made these exact same predictions if all we had was information on the generosity? All right. And remember, in the generosity scale, you're always showing how the person would react if they did have the money. All right. But we can make predictions about how someone would behave if they didn't have money by how they act when they do have money. All right. Okay. So let's see how you could use pKa's to make determinations or predictions about whether a certain acid-base reaction would occur. All right. So in this first reaction, we're showing this reaction right here, and this thing we're saying, okay, this thing, let's see if it could act as an acid, and this thing could act as a base. All right. Well, what we know about this particular acid is that its pKa is 4.2. All right. That means that it's relatively generous with its acid. All right. But we want to see if this ammonia is basic enough to grab that hydrogen. All right. So you might think, well, we need to know about the Kb, or that which describes how basic this is. But what we're going to do instead is we're going to think about, well, what is the Ka of its conjugate acid? All right. Well, the conjugate acid of ammonia is ammonium, and the pKa of ammonium is 10. So what these numbers mean is that this acid is much more willing to donate an H+ than ammonium is willing to give up an H+. In other words, this acid is much more generous with its H+ than this right here. Well, let's take a look at predictions that we made before. What we saw before was that things that we knew to be very generous, all right, would lose their money to essentially the conjugate base of acids that were less generous. All right. So we used this information to predict that this would happen. All right. Remember, Tom is the very generous thing. All right. And Sam, all right, because he's less generous when he doesn't have the money, he would end up being very greedy. All right. So what this means is that since this is a less generous conjugate acid, it means its base would be more greedy. All right. So we, using that information, all right, we know that since this pKa of this corresponding conjugate acid is high, we know that this reaction would occur. All right. So by comparison, let's ask ourselves whether this reaction would be predicted to occur. All right. We know that the pKa of this as an acid would be this. And we know that we want to see if this base right here is strong enough to grab this H+. All right, well, how are we going to do that? Well, instead of giving the pKb of this, we're going to think about the pKa of its conjugate acid, which would be this right here. And the pKa of that is about 4.2. All right, so what that means is that this is not that generous with its H+, all right, because it's got a relatively high pKa. This conjugate acid right here is relatively generous with its H+. All right, this conjugate acid is more generous with its H+ than this right here. All right, so remember, since this thing right here is relatively generous with its H+, that means that its base, all right, would be relatively ungreedy. All right, remember there's this inverse relationship. Things that are very generous when they do have money are things that are not very greedy when they don't have money. All right, so things that are very generous when they have the hydrogen are not very greedy when they don't have the hydrogen. All right, so what that would mean, since this acid right here has got a higher pKa than this conjugate acid over here, this would not be predicted to happen. So this is a very common rule of thumb that a lot of chemists will use when predicting whether a base is strong enough to essentially accept a hydrogen from an acid. And that is, if the conjugate acid of the base, if it has a pKa which is 2 units higher than the pKa of the acid, then it will take that hydrogen. All right. So again, the bottom line for why sometimes chemists will incorrectly state the strength of a base by referring to its pKa when they really mean that that's the pKa of its conjugate acid is that number of that they give tells you how strong that base is.